recording as well. So today we are now starting Rootlocus method, and then we are going to continue our progress of our course to design of the control system. But we know the problem. Problem is this. Problem is this. Now that is the typical control system. We have controller here, and we have actuator plus the system. Sorry about those. Anyway, so that is the system. Of course, we define those in S domain. Then we have an output. The output generally is controlled by a sensor which has got HS. This comparison is done, which is your wish, and that is the reality. And the difference between those is error. All are in S domain. Now the controller here, GC controller, might be K proportional or I integral PI or PD or the combination of those, which is called PID. I am also very much disappointed about your answer about PID, since it's already in your notes. It's an open book exam, so this is of course proportional controller. That one is proportional controller. Okay, integral controller we integrated, so this is all GC. Okay, this is all GC controller. Now for Rootlocus we use K only for Rootlocus. What's happening in Rootlocus is this. We are trying to establish the waveform of the poles, and if there are any zeros, poles and zeros. Of course there is a poles and zeros are changing with the constant value. So if you remember, I cleaned this page. If you remember the S-plane, which S-plane is something like this. That one is the imaginary, and that one is real value, which represent sigma, and that represents, of course, omega d. And assume that for a constant k value, your poles are located like this. But when you change k, your poles, this one is S1, for example. This one is S1, this one is S2, Bir de S3'yi buraya koyalım. S3. When you increase your K starting from K equals 0 to K büyük yazalım. Equal infinite, we are changing it. So it's actually starting, the curve is starting from the way I'm going to draw the curve. With change of K, the trajectory of the location of the poles is moving like this, starting from this point first, coming here, and then changing its direction there and moving. This is K equal infinite point. That is K equal infinite point, and that one, for example, is equal K equals 0 point. Buraya da koyayım bir tane. Bu da K equal 0 point. Hem burada bir tane daha olsun. K equal 0 bir tane daha olsun. Tamam mı? So then when you increase K step by step, follow my cursor please. When you increase K step by step, the poles are changing. Of course, you as a designer, you are selecting the point value of K for the best design figure. In order to do that, for example, if you select yeşille çiziyorum bir çeşit seçtiğimiz değer olsun diye. Mesela if you select those, that angle is beta, you remember that. So this is a certain zeta, which is not very bad. That one, remember omega d. That one is omega n, the amplitude of this one, and that one is sigma. Sigma. Sigma is minus, of course. You know that poles should be minus sigma plus and minus j omega d. S12. So you are, as a result, when you change your value of K from 0 to infinite, your poles means the roots of the characteristic equation are changing. When they are changing, you are able to select the best design point for you, best design K value for you. Of course, we all know that by looking at the stability part, you are not absolutely free to increase the K value. And you can see that for K increasing, that one, for example, that doesn't mean K infinite, for example. Probably K infinite somewhere far away from us. And when, for example, if you have a curve like this, neyse çizmeyeyim bir daha. It's going to be misleading. So the story is all about, if you have a controller which only the K value, the proportional controller is changed, you are going to see the location of the poles. This method is called root locus. I come back to the starting part of the course. When I was student, there were, or many years back, the MATLAB was not developed. Therefore, those curves have been driven by hand, have been drawing by hand. Of course, now computer is drawing it. But the books generally still explains how to draw it. Now, this is the general control system, but we should add if we add a K here, K here, so this means this becomes K GS over 1 plus K GS HS. Instead of 1 plus GSHS, you can see that in my cursor, it adds K. But this is a starting point. So delta is our characteristic equation. So if you look at delta, bunu siliyorum şimdi. Bunun anlamı kalmadı. Şimdilik. So assume there is no K here. This is a general starting point. This is your transfer function, and that is your delta, the characteristic equation. If GH, if that one is equal to 0, then GSHS should be -1. Who is going to interpret that one? GSHS should be -1 means that the amplitude of GSHS is 1, the angle of this one is 180 degree. Probably you would be feeling that you are not very comfortable explaining those 180 degree business. Look, what is E J pi? Cosinus pi plus J sine pi. Cosinus pi plus J sine pi. Cosinus pi kaç derecedir? 180 derece. 180 degree. What's the 180 degree cosine value of it? Who is going to answer it? I remember the trigonometric table. That one was cosine, that one was sine. And if the angle becomes 180 degree, 180 derece, cosine becomes -1. So that is -1 plus 0. So 180 degree reflects the minus sign here. Is it clear now? Ses gelmiyor. Çocuklar, trigonometri ben de yani ezberi sevmem. Yani ezber kabiliyetim yüksek değildir. O yüzden de hep defter kitap açık imtihan yapıyorum. Siz de ezberlemeyin boşuna diye. Ama bazı konseptler de var. Onları da bilmek lazım. There are some concepts You have to know that. That for example, the equation e to power j alpha is cosine alpha plus j sine alpha. So this one is equal to -1 if it is angle is pi. So -1 is represented by the 180 degree with the odd orders of it. Çift katı olursa, if it is a even order, it becomes 360 degrees. So we don't accept that one. It should be 180 degree and their orders, odd orders, tek katları. Anyway, the answer is this. Don't forget the main objective. The k is changing, so we are trying to obtain the trajectory of the poles of the or the roots of the characteristic equation. The by drawing by hand, you see those explanations. Of course, is necessary. Drawing by hand, we used to do that. GSHS amplitude should be 1 and the angle should be 180 degree. It is clear, I believe. So these are the handwriting methods. So you see, assume that I'm not going to spend too much time on this one, but just imagine one location here, for example, that is the so-called value of the curve, and then the angle of this one. These are the poles. Angle of that one. Angle of that one. That one is 0, by the way. This is 0. This is pole. This is pole. And this is pole. And those angles, total angles, theta, should be 180 or odd order of it. That is the rule. Anyway. Now we are adding k here. If we add a k here, then your control system GH becomes k times zeros, and n times, I'm sorry, m times m times zeros or n times poles. Okay, so delta here, delta is equal 1 plus GSHS, so 1 plus k times that, and the zeros, of course, and the poles. If that one is clear, we are going to move further. When the gain k varies, that is the main objective. K is varying from 0 to infinite. The roots of delta varies too, as I explained before. Thus, the poles of the closed loop system have a trajectory which is called root loci. Root loci. Method is called root locus. This method is called root locus. This is what we are learning. So in summary, what did you understand? Is this: we are changing k from 0 to infinite. Yazacağım buraya. K from 0 to infinite. We are going to give 0, we are going to 0, 1, 0.1, 0.2, 0.3, 1, 2, 3, 5, 6, 7, 8, infinite. So in the meantime, however, we have zeros of our system and the poles. How could I draw that kind of curve? if I write this is delta again, I come back. If you multiply poles with 1, both sides, multiply both sides with poles, then equality is not disturbed. So it's going to be 0 again. So if you come down, poles plus k times zeros should be equal to 0, while k is changing from 0 to infinite. I repeat, the poles, we don't know how many poles we have. Depends upon the order of the differential equation anyway. And the number of zeros also are decisive, but k is starting from 0 to infinite. If k is equal to 0, that term becomes 0, but this, in order to satisfy the equation here, should be equal to 0 anyway, you have to, s should be equal to your poles. So for equal k, I repeat, for equal k equals 0, k equals 0, your journey is starting from your poles. However, when k equals infinite, then only this, in order to make this term equal to 0, your system zeros should satisfy that one. So your journey is starting from the roots, which k equals 0, end up with zeros. Never forget that our main objective is to obtain the trajectory of the location of the roots. Location of the roots are very decisive. In second order system, which it was also an examination problem, we have seen that it decides the overshoot, it decides the settling time, it decides the rising time. So how fast your system would be, how less oscillating your system would be, are depending upon the location of the roots. Now, this is the general starting of it. With, of course, you are very lucky that MATLAB is drawing those curves easily. Control books initially explain how to draw the root loci by hand. Still, books are explaining by hand method, emphasizing that amplitude should be 1 and angle, total angle, should be 180, or the order of it, odd order of it. Okay, but MATLAB is easy. That's the problem. Now we have a system which is a second order system, and we have k here. K is a variable parameter starting from 0 and increasing incrementally to infinite. What kind of curve do we have? Your transfer function is equal to g over 1 plus g. That means k over s plus 2, 1 plus k over s plus 2, which is equal to k over s squared 2s k. Okay. Root locus, while the root locus is drawing the curve, you are not have to give k value. Okay. Sorry about that. Görkem Hanım, ben dersteyim.
Tamam hocam, görüşürüz.
Online. So you can see that the 1 plus GH is equal 1 plus K times 1 over S plus 2. So you are going to write this one. P is equal to, in MATLAB statement, P is equal to 1. Q is equal to S square is 1. 2S, 2 is coming here, and 0 here. Then if you write system equal to transfer function PQ, so you already store transfer function as well. And then if you write root locus system, the curve is going to be drawn. I know without doing it, it is not very easy to learn. So that's why I repeat. But first of all, I would like to show you. I'm going to draw that curve myself anyway. So I'm going to take the note here. What's our transfer function? G is equal 1 over S plus 2 and H is equal 1. That's the transfer function. Clean page açacağım. We are going to see anyway. Clean page. Now, system is this. Output, input, and comparison. Okay. So this system is like this. So the transfer function TF is equal G here is equal 1 over S plus 2. H is equal 1. So delta 1 plus GH. So if I draw here, so the one of the pole of the G, one of the pole of the G is located here, s equals 0, s equals 0. The other one is located here, s equal minus 2. So it's coming from here, okay? So GH actually is going to be minus 1. That is the rule. The curve is going to be like this. When these values also represent k equals 0, that one also k equals 0. When you increase k, the location of the roots are going to move like this. And they are going to come here, and then they are going to change its direction, and it's going to be something like this. So, for example, k equal infinite is going to be going up. Another k infinite de burada. K equal infinite. So the curves are starting its journey from the actual poles of the G, and then these are the transfer function poles, by the way, and the location of those are changing with increasing of k's. If I make this one is a little bit clearer, I'm going to come back to yeah, the journey starts from k equal 0, which are poles, and ends the k equal infinite with zeros. So how do you do that in MATLAB? You are going to you are going to give the p here zeros 1, and then q here gh, of course, h is equal to 1. GH is going to be drawn. That's, you can see that one here. Q is equal 1, 2, 0, s squared plus 2s plus 0. So 1, 2, 0. System equal transfer function PQ. Then you root lock a system is going to draw, computer is going to draw, and it's going to give you that curve. Now it is better to understand now the case. I draw it by hand, which is not very good. So it's starting. If I ask you, show me the k equals 0 value. K equals 0 value. Can you show me that? I repeat. K, geri dönüyorum. K equals 0 means you are in the poles. Your journey is starting from the poles. The trajectory is starting its route from the poles. What are the poles here? One of them is equal 0. The other one is s equal minus 2. So your journey is actually starting from that point and this point. When you increase k, then while increasing the k, your transfer function roots are located and then at a certain point it comes and join. That point reflects what? Neyi yansıtır? That point reflects a special case. What was that special case were about? You are not answering it. If two roots are if two poles are equal, it was a critically damped case. Don't forget that. The step response. You remember the step response. That theta, for example, I generally call it beta. This book is you can see that the Richard Dorf's and Bishop's book. This is also a very nice book. I picked that picture from there, and you can see that the this is a second order response with respect to the variation of the K. And you can see that this one, for example, which one is the better point? Which one is better, K2 or K1? Which point is better, K2 or K1? We have 12 students in our classroom. Which one is better, K1 or K2? First, you ask this question to yourself. What better is? Better means for step response, for example, less overshoot. Step response, less overshoot. Fast response, that means settling time should be as low as possible. What is sigma here, by the way? Evet, canlandıramıyorsunuz herhalde çocuklar. Bir dakika. Şu ekseni kullanacağım. Burası time. Time axis. Burası da şey olsun. Step response. Şöyle. Bu step response'ı istiyorum. Ama karşıma böyle bir şey çıkıyor. Pardon. Kırmızıyla çizeceğim onu. Bu bir step response. Şu TS. TS. Bu TS. Bu maximum overshoot. Tamam. That one TR, rise time. For this point, for example, For this point, O should siyahla göstereceğim. For this point, O should probably is going to be something like this. Since zeta here is near to zeta, cosinus theta is equal to, or cosinus beta is equal to zeta, so zeta here is very close to 0. For that case, this is probably 1, 2, 3. 1, 2, 3, 4. Yeah. 3 bölü 4 kaç yapar? 0,75. Neyse, yani 60 dereceye yakın güzel bir açı. So this K1 is much better than K2. K2 is the black curve, and K1 most likely is the curve of the green. K1 most likely is a green one, so overshoot less than 10%, and also settling time. This probably settling time is the same, since settling time defined by this point, defined by sigma. Evet. Büyük bir sessizlik var sınıfta. Hiç hoşlanmadım. Geri dönüyorum. If you have a system like this, all you have to do to write this statement and draw that curve. But you have to interpret it. Yorumlayabilmelisiniz. You have to explain which value of K you are going to select. By looking at the overshoot, by looking at the settling time, rise time, and things like this, you are going to select the best K value for this second order system. It is most likely that K1, which of course that one is also is equal -1, which is equal sigma. It is sigma is minus zeta omega n. This is omega n, by the way. Omega d is not shown here, but that point is omega d. That point. Omega d, this point. That omega n is already shown, and that point is sigma. Which is -1. Şimdi bir örnek daha vereceğim çocuklar. This is a second order system. Now, if you draw this one is a third order system. Poles are located S0, S-1, S-2. For this example, we have two poles. One of them is located in -2, and the other one is located to 0. And in -1, the curve, these two curves are separated. So if you draw the curves like this, so it's starting from this point. When you increase K, Then coming to this point, both poles are equal now. Then moving like this. Moving like this. These are k equal infinite points, asymptotic. K equal infinite points. So that value, -1, is symmetrical. That one is 0, that one is -2, and this one is -1. -1. However, for the next example, we have 3 poles. So we have to, of course, first locate those 3 poles here. I'm going to locate it here in order to make it easier for us. Of course, I'm going to show you the computer curve. Böyle bir şey olamaz. İğrenç. I'm sorry. Tamam, bu fena değil. Biraz eğri oldu ama. Şimdi bir tanesi, pollardan bir tanesi 0. The other one is -1. The other one is -2. Tamam mı? Now what's happening actually? These two poles couples and provide a waveform like this. They come here, they join here, and then the curve is going to be, computer is going to show you anyway. So that one is infinite k value. Of course, another one is here, k infinite value. But here also, this is going k infinite as well. So 3 poles are changing their locations while you are increasing the k value. And of course, which one is the best value for you? The best value is most likely, gene green'le çizelim bakalım. Şu değer, K'nın bu değeri, yani bir tanesi burada, bir tanesi burada, S1, S2, hem bir tane de burada tabii böyle gidiyor, S3. So these two are the approximately 60 degree, 45 degree. These are nice values. Reflects a good zeta values. So let's overshoot, of course. Which poles are dominant, by the way? Here. S1 and S2 are near to that means their time constant is higher, and also, however, S3 is a very fast, is far away from origin, is very fast, so diminish or disappear. The effect is very low. So S3 is a recessive pole, S1 and S2 are dominant poles, and your response is most likely, if you select K to produce S1 and S2, your waveform is going to be kind of nice step response, for example. Now I have a question. Can you find yeşil olmasın, o siyah olsun. Can you find the K value here? Which the curve is crossing the j omega axis. Another one is also bottom. Can you find the K value here? Sorry. Okay. I'm going to take a break. It's 10 o'clock. I'm going to take a break, and then when I come back, I'm going to ask you whether you have found it or not. 10 minutes break. 10 to 10. Okay. Let's take a break now. Merhaba. Merhaba tekrar. Şimdi you remember that I draw those curves by hand. So this is the problem. This is the problem. For those who join the classroom, I just repeat, for this kind of system, you're writing the MATLAB statements like this is going to immediately provide a curve like this. Of course, those grids and things like this, you have to give another additional information. However, you obtain those curves. And then while you are moving your cursor on top of it, you can see the value of k, you can see even, you can obtain the zeta, and you can easily decide which kind of k value is most appropriate for your application. But for second order system, no matter whether k is 0 or infinite, system is always stable since all the poles are located in the left-hand side of the S-plane. But for this one, it's a third order system, and if you write this MATLAB statement like P equal 1, Q equal 1, 3, 2, 0. You control it later, okay? System equal transfer function PQ, then root locus system. Buralarda noktalı virgülü unutursanız the curve is going to be drawn. Now I have a question. What's that 1320? What's that one? Bir kişi yazmayacak mı ya bu nedir diye? Nobody is answering, or open your microphone and say it. Where did I find 1320? Beraber yapalım. S kare artı 3S artı 2 çarpı S. O da S küp artı 3S kare artı 2S. 2S. S küp 1, S kare 3, 3, 2S 2. Of course, there's 0. There is no constant here. 0. That's the one. So this is the denominator of the G. P is the one here. You are not writing anything like K or something like this. when you draw it, you obtain that curve. So we are going to interpret that one. Biraz küçülteyim, çok büyüdü. Now, the journey is starting from poles for k equals 0, poles. Bir tanesi, one of them is 0. See here. The other one is -1. And the other one was -3, -2. Now, these are k equals 0 values. When you increase k, then the poles are going to, for example, k equal, then it comes here and then move like this. These are key, biraz daha küçülteyim şekli. These are key infinite values. And while it's moving like this, for this value, for this value, and for that value, for that value, and also for this value, for k is equal to 1.03. Okay, it is a nice value since it's 60 degree. Cosinus 60, cosinus beta is equal to zeta. So cosinus 60 is equal to karekök 3 bölü 2 idi değil mi? Kaç yapıyor? 1.72 bölü 2. Biriniz hesaplayıverin ya şunu. Kosinüs 60'ı. Bana makineyi çıkarttırmayın. Neyse çıkaralım. Evet. Çıkarttık makinemizi de. 60 kosinüs 0.5. Yanlış yapmışım. Siliyorum. Kosinüs 60 1 bölü 2 idi tabii. Point 5. Is not bad at all. Now I ask you, how do you find those black points? I might ask you in examination too. How do you find those black points? Where the value of k, where your system is crossing the omega axis. Neyse. Yani bir quiz açacaktım ama şimdi quiz'i açarken dosya kaybolur, maybolur. Onun için açmıyorum ama bundan sonra quiz hazırlayacağım. Pat diye açacağım. 3 dakika içinde cevap vereceksiniz. How do you find that when you use MATLAB, your cursor will tell you the value of k here. But what I'm asking you, how do you find it by hand? O zaman dinleyin beni. Transfer function TF is equal to, çok kalın, biraz incelteceğim. Evet. TF is equal to K over S plus 1 S plus 2 over 1 plus K over S plus 1 S plus 2, which is equal to K over S plus 1 S plus 2 plus K. Bu neye eşit? S square S to power 3 plus 3S square plus 2S plus K equal to 0. Değil mi? Delta bu. Delta equal to 0. Now we are Raoult's method. S to power 3 S square S to 1 S0. S to power 3 1 2 3 K. That one here 6 minus K over 3. That one is 0. And that 6 minus K, 3 times K divided by 6 minus 3, so it's K. So result 6 minus K over 3 should be higher than 0. So K should be lower than 6. So the result K should be lower than 6 or equal. Ben ters yaptım. Ters yaptım, bir saniye. I'm sorry. Ters yazdım. İkisini de ters yazdım. So if k equals 6, you can see that the roots are on the j omega axis, on the j axis. Nobody answered that question. I'm very much disappointed. Very much disappointed. It was very easy. You see what's happening, my son and my daughter. What's happening? Never think that whether this problem is going to be asked in the examination. Never consider, don't put that one in priority. What you should put, if I would become an engineer working in a control company, there are a lot of control applications going on, particularly in high technology, for example, the defense companies, high technology automotive companies, the other companies as well. So there are a lot of jobs available, and most of the jobs probably will be involving control problems. So if you do not have a clear idea about the control system, then of course either you are not going to be selected during the of course interview, either you are not going to be selected, or most likely when you start working there, you are going to realize that you know less than the other uh, colleagues of yours, and then either you are going to blame yourself, or you are going to blame myself, that probably you would think that I couldn't be able to teach you properly. So I'm emphasizing, always think, why do I learn this? In which respect this application might be used in other part, and things like this. Do not put knowledge in a very stiff clusters or files, which except only those files could be only opened in during the examination. That is terrible. You understand? Sadece sınavda açılacak klasörler oluşturmayın beyninizde. Her zaman dersin işleyişi sırasında veyahut da başka olaylarla karşılaştığında her zaman bu bilgilerle yeni bilgileri üretebilecek zihin yapısını geliştirmeye çalışın. Daha çok gençsiniz, beyniniz buna müsait. Türkçe söyledim bir kısmını, çünkü sınıfın bayağı bir içinde Türk öğrenci var, Türkçe. Diğerleri de biliyor biraz. So your brain is capable to do that. Okay. Neredeydik? Evet. Klasörümüze geri dönüyoruz. For the second order system, we have curves are located in the line here parallel to j omega axis. Therefore, no matter how big your k is, it's always stable. However, for the third order system like this, then the curve is going to be something like that. And you are free to select the best or the most appropriate, en uygun K value for your design. Don't forget that we haven't changed derivative, and we haven't used derivative, we haven't used integral. We are just using the proportionality constant. Okay. What about that one, for example? First thing, that draw that line. Of course, computer is going to draw it, but first of all, you have to think the journey is going to start from poles, and then it's going to end at 0. Now we have a 0. If you don't have 0, it's going to be asymptotic. Now I draw the curve. Simetrik olması lazım. Neyse. Şimdi bu nasılsa üstünde göstereceğim. So s squared plus 2s plus 3 has got two poles. One of them, buradan kopya çekeceğim şimdi. Evet, kopya işe yaramadı. Çünkü yani 1,5 falan gibi, imajiner kısmı 1,5 gibi, reel kısmı da 1,5 gibi çıkıyor. Geri dönüyorum. I come back. O zaman çözeceğim. S1 S12 eşittir. Eksi b bölü 2a eksi bölü 2 artı eksi karekök, işte orada karekökün içini buraya alıyorum. B kare 4 eksi 4 a 1 c 3 çarpı 3. O da eşittir 12 eksi 4 karekök 8. Pardon, karekök eksi 8. Şimdi onu alıyorum. Karekök eksi 8'i hemen alıyorum. Eksi 8 demek karekök j kare, kim büyütüyor ya? G square 8 demek. O da eşittir. Şimdi alıyorum. 8'in karekökü 2,8 çıkıyor. Bir dakika, doğru mu aldım? 8 karekök. Evet, 2,8. So S12 is equal -1 plus and minus C 2,8. Şimdi o zaman yerleştireyim bunları. So you remember these are the poles. So bir tanesi J 2,8 3 diyelim buraya. Şöyle 3'ü ayırıyorum. 1. 3 eşit parçaya böldüm aklım sıra. 2,8 burada. Öbürü eksi 1. O da burada. Demek ki bir tanesi burada. Diğeri symmetrical. The other one is symmetrical here. Bir tane daha olacak. Üçüncüsü nerede? Zero'da olması lazım o, değil mi? Nerede? Zero'da değil. Bir dakika. Neydi bizim değerimiz? Bu çocuklar, bu şimdi ben buradan bakıyorum. Bir tane S artı 2'de zero'su var. Onu koyacağım şimdi. S artı 2'de bir zero'su var. Şu 1'di, bu 2. Buraya bir zero koyuyorum. Yuvarlak. Eksi 2'ye. Ha, burada önümde zaten ya. Bunun kökleri de bunlar. Tamam. Yani buradan başlayacak. They are going to start the journey and end up with this one. Of course, I know the result. The result is going to be something like this. Did you understand what's going on? I have obtained the poles of the transfer function, rather the poles of the G, and also the zeros of the G, or GH, by the way. 1 plus GH should be equal to 0. That means GH should be equal to -1. And root locus draw that curve. The curve is going to be something like this. Starting those points, coming here, and then going at k equal infinite. K equal infinite. Bu ne peki? That one is k equal to 0, k equal to 0. That one is k equal to 0. When k equal to 0, these are poles. But here you have two poles, therefore the curve is going to continue. Is going to continue through that line, and k equal infinite of this one. So the trajectory of that one is moving like this, coming when you increase the k, and then turning. One of them is going to 0, the other one is moving. So of course, imagine to draw those curves by hand, but computer is easily draw the curve like this. You can see that the root locus plot is like this, and of course still they are looking for the angle. Don't worry about the angle now. Computer is going to draw it. But we are going to consider the angle for the next hour course or something like this. So that curve, the best point is the zeta 0.7 line. You can see that. How many, what's the angle of it? I just write here. Ask the question, what's zeta? How could I reach? Zeta equal 0.7. Şu açı beta. Kosinüs beta eşittir zeta. Beta eşittir kosinüs eksi 1. Zeta 0.7 olduğuna göre 0.7. Şimdi buradan hemen bakıyorum. Kaç dereceye karşılık geldiğini bulacağız. .7 inverse cosine 45 derece, 45,5 derece. 45 derece beta. The best angle here is 45 degree. So, but if you select the point here, for example, what's going to happen? Of course, you are going to reduce the overshoot as well, further reduction. But your system also is going to be different. For that one, for example, for this one, if you select the point here, that means it's a kind of critically damped case. Anyway, so that is the best point, by the way. That's the best point. For that one, it's becoming more and more difficult. So we have 1, 0, but 1, 2, 3, 4, 4 poles. So it's going to be 4 poles should be defined. I'm not going to calculate those. One of them is biraz büyüteyim. One of the pole is here. Kırmızı olsun gene. One of the pole is there. The other one is here. However, we have 4. These are the points. These are the poles of this equation here. So satisfy that one. These are the points start k equals 0 points. So when you increase the k, sum of the curve is going to move like this and end up at 0, s equal -3 here. Sıfır eksenini görmeniz lazım, bir dakika. Gördünüz mü 0 ekseni? Şimdi şurada I'm going to ask you a question now. If you answer that question, I would be very happy. If you can't answer the question, I'm going to be sorry about myself and yourself. That point here and this point here. Why these points are important? Since this red curve, while starting from, biraz ince yapsaydım, neyse artık gidiyor. Starting from those points, and then while you are increasing the k, it's moving like this. This is k equal infinite point. The other one is also k equal infinite point. That one is also k equal infinite point, this one. So we have 1, 2, 3, 4 poles. That means we have 1, 0 here, 1, 0 here. So, but there are 3 left. We have 4 poles, 1, 0. Therefore, 4 minus 1. That means 3 asymptotic values here. What about those black ones? Why those black ones are important? Why those black ones are important? What's the k value here? What's the K value here? Points of changing of what? Abdurrahman. Abdurrahman mı demişti? Bakayım. Yes, Abdurrahman. Points of changing. Changing of what? Şu line'ı da çizeyim. Zero line'ı da çizeyim. I'm going to draw the zero line. Probably it will help you to answer those questions. This is zero line. This is y-axis. Birisi daha bir şey yazdı. These are not the proper answer of the question, Abdurrahman. Thank you for your attempts. But why those K value is important? Is there any other to make a comment about this? Ya biz boşuna mı yaptık çocuklar? O Raut Hurwitz'ler bilmem neler. Beyond y-axis right hand side, if roots are moving in the right hand side, system is unstable. So this is the stability limit. Beyond that, it is unstable. The best operating point probably obtain the best operating point here. Soru. Bu mu? Aynı eğri olsun. Bu mu? Aşağı doğru da onun simetriği bu. Simetriği bu. 60 derece aldım aşağı yukarı. İkisi de 60 derece bakın. Aynı line üzerinde. Yani 60 derece işte 0,5 zeta eşittir 0,5 both of them. Zeta is equal to point 5. Reasonable. Which one is more active or dominant? We have 4 poles. I select the K value, which I don't know, but it's giving us these 4 poles. Which one which one I should take into consideration? Which one I can neglect, in other words? Although this is not far away from origin. That is the origin, by the way. That one is the origin line. Zero line. This one is zero line. I asked before, I asked that why these are important. You haven't answered. When for a certain value of k, it becomes, these are the stability limits. But for those red ones, we have 4 poles. Which poles are dominant? Which poles could be neglected comparing with those? These are the dominant poles. These are, okay. Not zero axis, of course. I'm comparing the red ones. Abdurrahman, I'm comparing the red ones. Black ones represent the, probably for black ones, these I don't know, but most likely also there are some poles here too. Just uydurarak söylüyorum. Tamam. Yani black K'nın belli bir değerinde for I don't know K is equal KS yazıyorum stability anlamında. KS. Tamam mı? Burada stability'nin limiti. But the red ones journey started from this point. Journey started from those points and come like this. And for that one too. Moving and reaching to those points. Okay. And for that one as well. So those who near to origin, that is your origin, are dominant poles. These are dominant poles. These are not dominant, although it might have an effect not far away from other poles, but these are dominant poles if you consider it as if it's a second order system. So I'm going to make a brief summary now before the break. The location of the if system is the first order, and also tau1 or t1 is the time constant. Location of the root, you can see here, is over there, and the motion of the while you are increasing k, motion of this pole is in this direction. If that one is equal one pole at origin, motion is similar. This one is starting minus 1 over tau. This one is starting 0. However, for second order system, if a system like this, first start this one pole is located at 0, the other pole is equal 1 minus tau 1. Eksi 2 diyorduk hatırlarsanız. S artı 2 dediğin zaman zaten tau 1 bölü tau çıkıyor orada. You obtain the 1 over tau. So and the system is always stable. You remember that. Or instead of S equal to 0, you have 2 poles one of them is, for example, S artı 1, the other one is S artı 2, for example. So one of the pole was -1, the other one is -2, which represent if you write like this, these are time constants also of this first equation, T1, T2. And of course, trajectory is again parallel to j omega axis. It's a second order system parallel to j omega, and always stable. Is nice. But for the third order system, if you have 3 poles located here, in between those, it's separated and moves to the right hand side of the, for higher values case, k, when you increase k step by step, start from poles, journey starting from poles and then increasing, and then of course there's a third pole which is a very recessive pole, doesn't have any effect, and that pole also moving in this direction. If it is if that one is, one of them is 0, you can see there is a S here. So the curve is nearer to the origin, and the value of k is, for example, these are not for those k values represent unstable part. Just select it like this. Doesn't matter. It could have been selected for small value of k. It might be in this point as well. Of course, we are not stupid to select a k value to give us unstable operation. So we are going to select those red ones, for example. Even that one is oscillatory. I would select all like this. 60 degree, 45 degree, between those is giving us the best. Which one is faster, by the way? That one or this one or this one? Faster. If you move away from origin, it becomes faster. We also remember the TS for the second order system, however, TS settling time was 3 over sigma or 4 over sigma. So settling time, if sigma becomes higher, settling times become smaller. So if I have a curve like this, for example, of course, that is the sigma. That is, of course, this is the sigma of the blue one. Of course, this one is faster than this one. Far away from origin means faster. Buna kafa karışmasın. Silelim ve devam edelim. There are other curves as well. The effect of 0 could be clearly seen here. If you put a 0 here, look, one of them is S square, and also one pole here is located. I will show you. Follow my cursor, please. One double pole is located in S origin, S equal to 0, and one of them is located 1 over minus 1 over tau 1, which is sigma actually. And also you have 1 0 1 0 here. So this zero couples with this pole, and the operation points are moving in this direction and ends up with 0. And however, these curves are in the stable part, but very near to origin. On the other hand, if zero, if we do not have double pole here, we have one pole here, one pole there. These two poles are coupling and producing a similar waveform, but a bit far away from. So it's faster, of course, far away from j omega axis. Therefore, this one is better, but this zero is still coupling with this one. So the curve is something like this. I'm going to throw that curve. So these are starting from there and moving like this, symmetrical. Of course, the operating point you are going to select. This is also always stable. That one is always stable as well. Zero, the effect of zero is such that always takes the curves in the stable part. That one, can you predict the waveform of this one? Can you predict the waveform of this one? K over S square. It is oscillation. It's always solution is j omega. So it's a cosine or sine function. That one is not very nice. That means this system is always stable. So one pole is moving in a stable part, the other poles are moving in unstable part. Therefore, this system always unstable without providing some kind of um, proportional derivative and integral action. This particularly you need the derivative action to get rid of this unstable waveform. That one is unstable too. S square and also S to 1 plus 1. Of course, one pole is located here. However, the other double pole is located in origin. So you have three poles. While you are increasing your K, the poles are moving in this direction, that direction, and that direction. Then it's going to be, of course, unstable solution. That one is also unstable. Three poles located in the origin. How many poles do we have? How many zeros do we have for this curve? Bir şey açacağım çocuklar. Quiz açacağım. Look at the picture. Transfer function is in the left-hand side. I just open up the You have 1 minute to answer. We have 4 answers, 5 answers. Hurry up, hurry up. 6 answers, 7, 8 answers. Hurry up. 9 answers, 10, 11. Thank you. Thank you. Hurry up. We have 21 students in our class, or 20 students in our classroom. Also, we can understand who is sleeping, who is following the course. We have 11 answers now. The rest probably couldn't be able to decide, or they are not in a classroom, so their friends are sending them email or WhatsApp message. Hurry up, you answer it. Okay. We have 11 answers. It's very disappointing. I'm closing the system in 10 seconds. Those who couldn't be able to decide, send it whether correct or wrong. Don't be put yourself in a out of classroom. So I regard that those who cannot answer it, or who sometimes some people have problems with internet, but generally speaking, that means they are not in the classroom. Okay. Have you seen the result? Can you see the result? 10 people say we have 3 zeros and 1 pole. Sorry, 3 zeros and 2 poles. What's that one? By the way, can you see the result? Bir cevap verin ya biriniz. Can you see the result? Yes, all right. Thank you, Abdurrahman. Yunus Emre, thank you. So you said that you said 10 of the classroom said that we have 3 zeros. However, you can see that 1 zero here, another 0 here. We have 3 poles. Probably you cannot understand the difference between poles and zeros. I realize that one. But I wonder, I'm going to find that the only person who answered correctly, thank you for him. I'm going to see his name now. Ozan, thank you. Ozan Akkoç said that we have only we have three poles and 2 zeros. Thank you. There is someone who put first correct answer, then change it and make it wrong. I don't know who was he or she. Anyway, however, Abdurrahman Efe Korkmaz, Adel Bayraktar, Ahmet Orabi, Ali Umut Terzi, Deniş Münir, Hilal Bassam, Hilal Akra, Halil Hatim, Muhammed Necati, Omar Şuvakani, Körk, Peki Körk'e niye oy vermedin Abdurrahman? Ya da Efe? Cevap bekliyorum Efe. Ama bak söylüyorum. Diyorum ki cevap vermeyenleri ben sınıfta yok sayıyorum diyorum. Belki İngilizcemden mi anlaşılmıyor? Ne oluyor? Burada olmayanlara ben iyi gözle bakmıyorum. Açık söyleyeyim. Oy vermeyenlere iyi gözle bakmıyorum. Seni anladım. Sınıftasın. Başka böyle sınıfta olup oy vermeyen var mı? Is there anyone who is in the classroom but couldn't be able to answer? Yunus Emre Çelebi, for example. Omar Şuvanti, Muhammed Necati saydım. Bunlar oy vermedi. O zaman ben de diyorum ki bunlar oy vermediğine göre iki şık var. Bir tanesi uyuyor. Niye basmadın Ali Ümit? Şey mi? Yani zor mu bu ankete cevap vermek ya? Yani herhalde kolay ya. Ali Umut da sınıftaymış. Neyse, üzülüyorum. Bak açık söyleyeyim, üzülüyorum. Evet, şimdi tekrar devam edelim. Bunu kapatıyoruz. Ha, o bir kişiyi de merak ediyorum. Önce doğru cevap verip sonra değiştirip şeye döneni merak ediyorum. Kimdi o? Artık neyse. Ozan, tekrar teşekkür ederim sana. Sınıfta tek doğru cevap veren. Yani Allah aşkına şu iki tane zero, üç tane de pol olduğunu you clearly can of course all of you the origin Arabic Allah aşkına means that I'm very surprised that almost nobody answered correctly. We have two zeros and three poles. Evet, gidiyorum şimdi. One zero, one zero, one two three four poles. Of course, some part is stable, some parts are stable, other parts are non-stable. On dört ne ya? Ha, 14. 14 burada. Şimdi söyleyeceğim 14. 14. Sen Abdurrahman, sen yorumla bakayım. Aç mikrofonunu yorumla. Tamam, Ozan yazmış zaten. Diyor ki Ozan, bir 2 3 4 5 tane pol var diyor. 2 tane de zero. There are five poles, two zeros. Correct. But I expect you also make a comment about this one. Make a comment. Comment is this. Comment is this. That part is important since very near to j omega axis. The other part, these are recessive poles. The effect of the poles are not important, but here it is. So for k equals 0, that one and that one. When you increase k, curve is moving. But stop here. Don't increase further. So stop there. If you increase further, so it's going to be oscillatory. And when you reach to this point and that point, which I always put it black, these are black points. For black points, it becomes unstable. So remain for certain value of k unstable, then gets into the stable part as well. So you can see some poles here, but of course very oscillatory. I'm not happy about those poles. I hope you understand that. Bir tane daha var mı burada? Evet, yok. Bitti. Şimdi çocuklar 11.30'da ben bir Avrupa Birliği Batarya Konferansı'na gireceğim. Dolayısıyla şimdi ara vereceğim. Fakat gelecek, Muhammed Seyit hocanız gelecek ve size MATLAB uygulamaları yaptıracak. Şimdi ona da bir mail atacağım ya da telefon ederim muhtemelen. Ben çıkıyorum diye. Ara ver. Don't leave. Yoklama yapmadım daha. Evet. Herhalde telefonu çekmiyor. Laboratuvarda bazen çekmiyor onun telefonu.
Aradığınız kişi telefona cevap veremiyor. Tercihiniz üzerinden mesaj bırakmak için bir tuşlayın. Beklediğiniz vergiler dahil 2 lira 50 kuruştur. Anonsu tekrar dinlemek. Tercihiniz üzerinden mesaj bırakmak için bir tuşlayın. Beklediğiniz vergiler dahil 2 lira 50 kuruştur.
Evet, yoklamamı alayım ben. Yusuf, Selim, Yunus, Emre, Erdoğan, Çelebi böyle gidiyor yukarı doğru. Ondan sonra en ön isim de bir kazasız belasız şunu bir kaydedelim, kopyalayalım. Yapıştırdığımı da göreyim. Don't leave. Muhammed, şimdi ben 11.30'da bir Avrupa Birliği toplantısına elektronik olarak bağlanacağım online olarak. Çocuklara ara veriyorum bir 15 dakika falan. Sen kaç gibi başlayacaksın? Ona göre söyleyeyim, şimdi sınıftalar zaten. Duyuyorlar bu konuşmayı. 40. Tamam. You have 15 minutes break and 11:40 the MATLAB application is going to start. Is that all right? Bir dakika. Tamam. Tamam, okudular. Hadi görüşürüz. Sağ olasın. Okay, I have already taken the attendance list.
Hello, everybody. We will start now. Does everyone hear? Okay, some students are here. Right. Okay, let's start then. Okay, so let's start our lab. So we did step responses last labs, right? The peak time, overshots, and so today we're gonna do the step responses again, impulse response, ramp response, and we're gonna observe some responses to arbitrary initial conditions. So first, let's start with step response again. Let's do a step response first. What? Let's close steps. Okay, so first we again define your time domain. So now let's again we define our numerator and denominator. So let's see, we're gonna use two systems in this one. So we're gonna call the first one is nominator, nominator 1 and nominator 2. First one, let's say 100 to 1000, right? So denominator 1. Let's say let's make it denominator. We can use one denominator for both systems, so you can just define one. Here, let's find our nominator 2. Let's call this. So in a live script format, you can write your codes, but you need to add the dot comma. All right. So now, first system, let's say system 1. You can just get transfer function. Then, and as you remember, you open the bracket and then write your nominator 1 and dot your denominator, right? And for the system 2, we can again write it like this, and then your transfer function, open bracket, your nominator 2 and denominator. So we define only one denominator, and we can use in both systems, right? As the, like, you can define it for denominator like this. Okay, let's first y1 for the step response. We just write step, or it will take the step response of the system 1 first, and then you need to open bracket system 1 dot and for your time domain and t. And for the system 2, you can take it again y2. All right, and then step response for bracket system2 dot t. And then now we're gonna plot this. For plotting it, you just write a plot function, and then you just open your bracket. For the first one, first system, you just define one y1. We define it, and then you go comma t, and then for the second system y2. right? So let's go, and then you repeat, test that, and then you can add title to your graph by just writing the title. For example, let's say you can write this one will be unit step response, unit step response. Then you can write the labels. Let's say X label for first. Open bracket, you add your dash, and then for the X label, it will be our T, time in second. And then you write your Y label. Okay. For the Y label, let's say we have a XT and YT. XT and your YT. All right, like this. Okay, now we can add a text in a graph, for example, like this. And then you can define where the text will be in your graph, so you can specify the points by just writing the points, and then in x-axis and y-axis. And then for the which one, let's say the first one will be our xt, and we can just simply write xt, and we will see it in the graph again. And text for the yt, let's say for the yt, and then you can specify the points again here, like 0.7, comma, and then let's say it should be 2.35. Okay, now let's run our section here. Oh, what is it? Oh, we forget a comma here. Right. What is it? Okay, so this is your unit step response for the system that we defined. Your numerator and denominator, you can create a two system transfer function, and then take the both transfer function of them. We get we plot, as you can see, the unit step response, and then you can define your xt and yt. We can add labels. See, this is your labels, t seconds, and then xt and yt. And then by the text, you can simply add your xt and yt in a graph. Like say we define it here. Yeah. Any question till here? We define our system, we get the step response, and we plot it, and we add labels to our graph. All clear till here? You should learn how to get transfer function and the step response. Okay, let's go to do our second one. So now we're gonna take a look for the impulse response. Yeah, we can just for the impulse response, again, we need to define your numerator and denominator again. Numerator, your denominator. Let's say one. Just define it, and then for the impulse response, you just write simply impulse. This function will just take the impulse response of your system, and in a parenthesis you need to define your system again. We define numerator and denominator. You just write numerator comma denominator, and we'll just get your impulse response of system. I need to add grid, and then we can add title again, right? Open parenthesis, and you can write your title for the graph. Let's say unit impulse response. Yeah, so this is how you get your impulse response of a system. Let's define denominator, and you can just run it simply. Yeah, this is your unit impulse response. So basically, the response of your system to a impulse, unit impulse. Impulse is a zero function. The signal is zero everywhere, but its value is 1 at 0. The impulse response. Okay, so now we get step response, impulse response. Okay, now let's take a look at the ramp response first. For the ramp response, let's again clear out that sheet. Clear the data sheet, and then first we need to again define our numerator and denominator. For this one, let's say 10 to 4. Come on, your denominator. So again, you need to define your time domain. And then now we're going to take a step response, and then we're going to plot it again. First, you define your system, then you get step response, your numerator, denominator, and the t. All right. So let's plot it. Need to write your time domain and your function. You add grid, and then you can again write your title and labels for the graph. This one will be unit step response again. Okay, let's add labels to our graph. For the X label, let's say it's for the time. This one is second, and the Y label. For Y label, our output. Sometimes live script is not working that way. it's like that. Wait. Oh, we forget equals here, guys. Okay, this is your unit step response. I'm saying why it's not working. As you can see, you take unit step response, we add labels, seconds, and for your output, this is your unit step response. So let's ask you a question from the last lab, the last week. We define as for the overshots, settling time. Let's say in here, what is the overshot value approximately in this unit step response? Anyone remember what was the overshot? How about the settling time? Anyone remember the settling time? No? Okay. Overshot value is the value which past our steady state value. Here is the unit step response is 1. Here, this is your overshot is about 2.2. This is overshot value. Settling time, that we define it as the time that our function takes to get a steady state. It's around here somewhere. So it is 3.8 seconds or something. So review the previous labs, so don't forget it, all right? Okay, now let's take a look at the ramp response. All right, how we get the ramp response? Okay, let's clear it first. Again, we're gonna define our numerator and denominator. Okay, let's call this 10 to 4, your denominator. Okay, for the ramp response, we're gonna take a step response or our system first, all right? Numerator 1, denominator 1, and then your time frame. Okay, so let's make it denominator 1. Okay, now we're gonna plot it first. We're gonna take a step response of system, and then we're gonna plot it, and then we're gonna take the ramp response of the system. So first, we're gonna do it like this. For time frame for the first and time frame for the second. Then we're gonna plot the step response by the dash simply. All right, and then for the system, you write your system in y1. All right, and then for the ramp response, we're gonna add our vector here, and then we're gonna define our axis for the v-axis. Okay, now you add your grid, and then you can now add your title here, and which will be ramp response, but this is unit ramp response. So unit ramp response, and then you can get X label and Y labels. So name it P second, and then Y label. This is unit ramp for the inputs and outputs. Inputs and outputs, let's say. Oh, we didn't define our T. Let's define our T. Yeah, so this is how you get a ramp response of a system. First, you define your transfer function, you take a step response, and we plot our transfer function by the dash. As you can see here, this is step response of our system. This is your step response of system, and the other one is your unit ramp response, right? And then that's how you get your unit ramp response. So is it clear till here? We get our first we define our unit step response, we get the impulse response, and we get our ramp response. Is it clear, guys? The responses, those one are important. We may ask in exam and will be in homeworks. You're welcome, guys. Have a nice day and see you next week. And study to the previous labs. I couldn't get any answers to the questions. What was overshot? What was settling time? Just study with the previous ones. Okay, see you guys. Have a nice day.
مرحبا محمد جو.
Yeah.
Oh, tamam. Thank you so much. It's gonna be
Yeah,
like a
welcome.
quiz or something like that?
I don't know. I'm thinking about it still, but I'll announce it when we have decided with Nejat Hoja.
So it will not be written in the final exam or something.
Yeah, Nejat Hoja may ask question about MATLAB in the exam. Can be.
And we have to ask
maybe.
like a code or something like that?
Yeah, he may give you a transfer function, ask for the responses, show it with your codes.
Nice. But it must be, or it will be like a quiz or separated exam for MATLAB, something like that, right?
No. If it will be in exam, he will ask for the MATLAB codes. You just write MATLAB codes on the exam sheet.
So it will not be.
Or,
Tamam, you will announce it. Tamam.
yeah, and we
No
have
problem.
a lot of weeks, so I'm thinking about doing the quiz in the last weeks before the final exams.
Tamam, nice.
Yeah.
Hello, Hojam.
Thank you. Have a good day.
You're welcome, Ernest. Yeah.
Hello, I wanted to ask, is the attendance necessary for the lab parts of this course?
Sorry?
Is the attendance necessary for the lab parts of this course?
Yes.
You take attendances?
Yes, I take attendances.
Because the last couple of labs, I was not attending them. because I thought
Yeah.
there's no attendance for the lab parts, and I thought there's no attendance. So what can I do now for the missed attendance parts?
You get missed points.
Huh. I mean, fair enough.
Yeah, there's nothing much you can do. Yeah.
All
Just
right.
watch the previous one so you don't miss anything.
Hopefully.
Hopefully.
All right. Have a nice day.
Have a nice day. Well,